So let's do an example of an Airy isostatic balance. So let's say we have continental crust here in one column. We have mantle. And then we have a mountain. This is a mountain sticking up above the surface of our continental crust. This mountain is also made of continental crust. But if we take an Airy type view of the world, then it must have some compensating root. And the way Archimedes' principle, or isostasy, works, it says that if you add up the weight of column 1 and add up the weight of column 2, they have to be equal. So the pressure here and the pressure here have to be equal. So let's assume that column 1 and column 2 have a width and a depth. So width this way and a depth into the void equal to 1. And so we're going to ignore those. And let's then calculate what the weight of this column would be. Okay, so this is air, continental crust, and mantle. We're going to take the density of air as 0, and we're going to ignore air. Continental crust will have a mass of 2670 kilograms per meter cubed. More importantly, we're just going to call it rho C, rho continental crust. And then the mantle will have rho M. Okay? The mountain is all continental crust, and we'll get to that in a second. But okay, let's calculate the pressure. So any pressure at depth is rho G times the height. Okay? So let's take that principle and we'll say, okay, what's the weight of the air? Well, it's rho air, height, A1, which is equal to 0. Excuse me. Rho air times A1 times G. Well, rho air is 0, so this is 0. Then let's take the weight of the continental crust. We're going to add to this. That's rho C times this height, which we're going to call C. We're going to call the thickness of the continental crust, the normal thickness of the continental crust, C. And so we have rho C times G plus this height, which we'll call B. And that's going to be rho M, because this is the mantle, times B times G. So the total pressure in column 1 is effective air, which is 0, the effective continental crust of thickness C, plus the effect of some amount of mantle of height B with a density of rho M. Now, isostasy says that the weight of this column has to be equal to the weight of column 2. So let's figure out the weight of column 2. Well, that is all one density, and its height A1, C, and B. So we've got, we'll do it over here. So the weight of this column is rho C times A plus C and B. And now, this gives us total pressure here, and we can set these two equal. And if there's one of, times G. And if there's one of these A, B, or C we don't know, we can solve for it. So let's say we were given the height A and the height C, and we wanted to know what the depth of the compensating root for this mountain would be. And this is the kind of thing we might run into in an actual situation, in that we can measure the height of the mountain. We have seismic data maybe for average continental crustal thickness. And then we can estimate what the root of the mountain belt would have to be to compensate it in an Airy fashion. So we can set these pressures equal. So we've got rho C, C plus rho M, B, all times G is equal to rho C times A plus B plus C times G. Obviously our G's cancel. And now we're going to solve for the thickness of the root, which is B. Notice that I use the same thickness for the mantle and the root because I chose to calculate the pressure in each column at the bottom of my root. Okay, so the only thing here is mantle, the only thing here is continental crust. You don't necessarily want to choose a depth here because now you have an extra thickness of mantle below your continental crust that you don't know. Okay. So what we can do here is rho CC plus rho MP equals rho C times A plus C plus rho CB. I just separated out the B because that's what we're solving for. Okay? So we get rho M minus rho C times B equals rho C. Now the C's cancel here times A. We divide this over, we get B is equal to rho C over rho M minus rho C times A. So what this tells us is that the thickness of B is a factor of the excess mass of the mountain divided by the difference between the mantle density and the crustal density. So this is basically an expression of Archimedes' principle. The height of this root, or the thickness of this root, has to balance the mass of the mountain above by displacing a certain amount of mantle.